Good morning, everybody. Sorry about that. And hopefully you guys can all hear me. Let me know if you can hear me. I'm going to try to remember each time to ask if you can hear me. That way I'll know that the chat's turned on as well. So good morning. Before we start talking about physics, I wanted to mention again the Science and Math Peer Tutoring Program, which is now up and running. This is the website for it. There's a link to it in Canvas. And as you can see, it's a little bit hard to see on the screen. The writing's very small, but there is tutoring for physics and math and chemistry and biology courses, mostly first-year courses, but also some second-year courses like organic chem and genetics. So if you're ever looking for extra help, were they very helpful? That's good to hear. They are students who took these courses, got very good marks. Most of them got A's or A+ in the courses they're tutoring for. So they're really good resources to go and talk to if you have questions. And you can see they have lots of hours on basically 5 days a week. So before we start on physics, does anybody have any quick questions about anything? Yes? Ashley, do you have a question or no? Okay, well, I'm not seeing any questions, so we're going to go ahead and get started. And again, Rasul is here to, okay, Landon, you have a question? You could put it in the chat. Let's have a look real quick. No question? I'm going to start screen sharing my other application. Okay, because I don't see a question yet. Okay, so if Landon, if you do have a question, hopefully, so the Canvas link, the Canvas link for the peer tutoring, that's under, you'll see there's a whole module for peer help and study skills. Okay, so what are we going to talk about today? So we're moving on to chapter 3, more material. We did vectors last time, right? So now we're going to move on to projectile motion. So you probably know the second pre-lecture was on 2 topics. It was projectile motion, and it was also circular motion. So what we're going to do is do projectile motion today, and we'll do circular motion and maybe a little bit more projectile motion on Friday, because notice there's no pre-lecture for Friday. We won't do more than 2 sets of pre-lectures each week. So here we go, projectile motion. So what is projectile motion? Essentially, it's a fancy name for any time you throw an object and you give it a horizontal velocity component. We're essentially going to be looking at, most of the time, just the surface of the Earth, where we know our acceleration is 9.8 meters per second squared in the downwards direction. And the main thing to remember about projectile motion is we're going to have this constant downwards acceleration. All right, and we're typically going to define plus y to be the upwards direction and plus x to be the direction you're moving in. And we're pretty much in this class not going to worry about air resistance. So we might talk about it a little bit, but we won't do calculations with it. Okay, so for today we're going to talk about the situation where there is no air resistance. Okay, and so what do we have for projectile motion? What defines projectile motion in physics? We have the horizontal part of the motion, okay, parallel to the surface of the ground. And what do we know for our horizontal motion? We know that the x component of this acceleration is 0. there's no x acceleration. We know that because there's no x acceleration, the y component of, sorry, the x component of the velocity is constant. Okay, so it doesn't change. So that means that the final x velocity equals the initial x velocity at all times. And then that leads us to having only one real kinematic equation in the x direction, which is the final x position equals the initial x position, x0 at time equals 0, plus the initial x velocity, v0x, times the time elapsed. Okay, so that's what we have for horizontal motion. And then, so that's parallel to the surface of the Earth. And then vertical motion up and down, which is perpendicular to the surface of the Earth, right? What do we know? We know that the y component of the acceleration, the vertical acceleration, is always equal to minus g, where g is our 9.81 meters per second squared. So because of that, we use our constant acceleration formulas. So our final y velocity at some later time will always equal the initial y velocity minus g times t, the time elapsed here. Remember, t here is always the time elapsed because we're most of the time going to start our motion at time equals 0. And then we have our position as a function of time in the y direction. Final y equals initial y plus initial y velocity times t minus 1/2 gt squared. And then we also have that fourth formula, the one that's basically is velocity as a function of position, right? Which is the one you would use if you don't have time and you don't need to solve for time, right? So like I was saying, we have things that are constant here. The x acceleration is constant, always equal to 0. The x velocity, velocity in the x direction, is constant, okay? And the y acceleration is constant. It's always equal to minus g, okay? And you can see I drew in a little downward arrow there to show you, to indicate that, and I stuck it not on the ball, but in the middle of the picture, because that's the acceleration everywhere in the motion, okay? So from the beginning to the end, when we're looking at projectile motion for the time being, all we're going to care about is from the moment after the object is launched. So we're not going to worry right now about how it was launched. You know, was it kicked? Was it pushed or thrown? We're going to just look at the time right after it's launched until right before it hits the ground or passes some point in space. So we're not going to worry about the collision of the object with the ground and what happens there. We'll worry about that kind of thing later. Okay? So for now, it's just what happens as the object flies through the air. So what I thought we would do is go and play around with this really nice PHYS, again, another nice simulation, okay, of projectile motion. So we're going to go find that one now. So let me see if I can find that. There's our projectile motion. There we go. Hopefully this will show up for you guys. There it is. Great. Okay, so this is the projectile motion PHYS. Okay, and this is a lot of fun. There's lots of things you can adjust here. You can change the size and mass of the cannonball. We're not going to worry about that ourselves. You can turn on air resistance. We will not do that today, at least. You can draw the velocity and the acceleration vectors, which can be quite useful. And you can also draw a force vector, which we're not going to worry about right now. And so, for example, if we start with our cannon at 45 degrees and our initial speed, which is the magnitude of the initial velocity, at 16 meters per second, and we fire it, and you can see what happens. And I'm going to pause it for a second here. Okay, so you can see it starts following this parabolic path. Okay, that yellow vector there, that's our acceleration, always pointing downwards, and the green vector is our velocity vector, the total velocity of the object, and it's always going to be tangent to the path. Okay, so you can see as we watch it go, all right, that velocity vector is always tangent to the path. Okay, and if we watch it go all the way from launch to landing, you get this nice, perfect parabolic path. Because as you'll see, if you combine the x and y as a function of time equations, you can get a y as a function of x equation that is a perfect parabola. Okay, so what can you do? Well, you can do things like change the speed. We can make the speed smaller and reset and fire again. And probably not surprisingly, with a smaller launch speed, the cannonball doesn't go as far. Okay, so that's one thing you can do, and it makes sense here, right? Okay, you can also change the launch angle. Right now we're at exactly 45 degrees. We can go down to say 25 degrees and fire it at the same speed we were originally at, 16 meters per second. And you can see for that very low launch velocity, we get a very, I'm going to turn off the vectors just for the time being. Okay, you can see a very shallow path. Okay, and then as you increase the angle, so say we do 35 and we fire it, probably not surprisingly, now we have a bit more y velocity and a bit less x. The y component is a bit bigger and the x component is a bit smaller. And so you can see it goes higher and it goes further. One thing we can do is take this little device and we can look at, and I believe it'll tell us how long it took. So the second one took 1.87 seconds to get there, and the first one only took 1.38 seconds to get there. Okay, I'm going to keep that there. So now we can keep increasing the angle. You can do 45, which we did before. I'm going to turn it back into normal so it goes a little bit faster. So there's 45 degrees. You can see it goes even further. Without air resistance, 45 degrees will give you the maximum range, the biggest distance. And then if we do 55, you can see it goes higher, but now it starts to follow a shorter path. And in fact, this one here, okay, went the same distance. The one at 55 went the same distance as the one at 35. And then again, we can go up even more. Say we do 65, okay, and we fire away. And now it goes much higher, and it lands at the same position as the 25-degree launch did. So there are symmetries here to this motion. And again, if we look at the times, okay, the later ones took even longer. So this is the time for the most recent one. It took almost 3 seconds. Because what's happening, what defines the time for this motion is how long it goes up and down, okay? Because what's happening is that constant y acceleration is causing the velocity to decrease as it goes up and increase as it goes down, right? So it becomes less positive as it goes up, and then it becomes more negative in velocity as it goes down, okay? And the acceleration basically tells you that that velocity changes by 9.8 meters per second every second, okay? So it's going to be decreasing by 9.8 meters per second every second on the way up, and then increasing, the magnitude will increase by 9.8 meters per second every second on the way down, okay? And so the larger the initial y velocity, like we could even crank this up to, say, 75, okay, the higher it's going to go and the longer it's going to stay in the air. And then there's lots of other fun things you can do with this FET. So I think that's all we're going to do. There's a link to all of the FETs in Canvas. I posted a general link, and then you can just go under it. How can you know which angle results in the longest angle? Which launch angle results in the longest distance and the longest range? You can actually solve for that with the kinematic equations. Okay. Basically, you can show that the maximum distance occurs for 45 degrees. I won't do that math now because that would take me the rest of class, and I don't think that's a valuable use of our time right now. Okay, so I'm going to stop this guy for now. All right. And now we're going to go back to our slideshow. Hopefully that will show up soon. There it goes. Okay. So here's an example of a projectile that's being launched. And so you can see it's got an initial velocity vector v0. Okay. And I've written down now, one of the first things you're going to almost always do with projectile motion problems is figure out the components, the x and the y components of the initial velocity vector. Okay, so the initial x velocity in this case is 9.8 meters per second, and the initial y velocity is positive 19.6 meters per second, so it's launched upwards and to the right. Okay, so what do we know about this motion? What can we see? Well, what we can see, here's a nice little picture to kind of show you what's happening with the motion. So so what we've done here, okay, so that we can analyze the motion, is we're starting here at the origin at x equals 0, y equals 0. Okay, and you can see we've got that initial velocity vector there. And then what they've done is they plotted the motion or the point of the object every 1 second. Okay, so what you can see is that after 1 second, the vertical velocity has decreased to upwards 9.8 meters per second. But the horizontal velocity has not changed. It's still 9.8 meters per second to the right. And so that makes the magnitude of the velocity, the total velocity vector, smaller, okay, as it goes up, okay, because the vertical component, like I was saying, decreases by 9.8 meters per second every second, all right? And then when we get to the top of the arc here, now the y velocity, just at that instant in time, the y component is equal to 0. Because it's decreased by another 9.8 meters per second, okay? But the x component is still 9.8 meters per second, right? It hasn't changed. That x component of the velocity is not going to change. Like it says, the horizontal component of the velocity is constant throughout the motion. So then after 1 more second, now the y component of the velocity is minus 9.8. Okay, it's pointing downwards because it's decreased by another 9.8, and that's flipped it in the negative direction. So that means the overall velocity vector now points downwards and to the right. And again, you can see these velocity vectors are always tangent to this blue parabolic path, the arc of the motion. Okay, and then when we hit the ground here, okay, we're now, again, x velocity has not changed, but now the downwards velocity, the vertical velocity is a negative 19.6 meters per second. That's the y component. So it's one interesting things to notice here are there are a lot of what we call symmetries to the motion. Okay, one symmetry, it says right here, is when the particle returns to its initial height, the y component of velocity is the opposite of its initial value. So it started with positive 19.6 meters per second up, and by the end, when you get back to the same height again, it's minus 19.6 meters per second. So it's the same size y component, but downwards. All right, and the same thing's true for the other two matching heights. If you look at the 1 second point here, right, you've got an upwards 9.8 meters per second, and if you go straight across at the same height, you can see later on at the same height, your y component is now minus 9.8. So that's a symmetry of the motion that will always happen. So sometimes in a problem, it's actually useful to use that symmetry, okay? Yeah, it's always reducing by 9.8 meters per second every second. Doesn't matter what the initial velocity is, because that's the acceleration acting. The acceleration is causing that decrease by 9.8 meters per second every second. Okay, so that's something it's important to keep in mind. All right, so, and you'll kind of get used to it as you go. So I thought we would do a poll question here to start, to get ourselves warmed up. So why don't you have a look at that, and I will start our poll. Move my computer over a little bit here. So Okay, so there's our poll now. All right, so the question is, so a golf ball is launched from the ground at an angle of 30 degrees above the horizontal, and it lands at a distance d from the tee. Okay, so assume it lands at the same height it started at. Okay, so it's a flat green. And the question is, at what other angle above the horizontal can you launch a golf ball at the same speed and have it land at the same spot? Yes, the polls are anonymous. So there's a question about, will the same angle end up at the same spot? So if you always launch at 30 degrees at the same speed, it will always end up at the same spot, yes. Provided you're launching in the same direction, of course. Yeah, so if you launch objects at the same speed from the same spot in the same direction, then they will land at the same spot. All right, I think we're going to do about 10 more seconds on this poll. So if you're not sure, go ahead and guess. All right, 5, 4, 3, 2, 1. And let's have a look at the responses. So what do we see? We see that the majority thinks that the answer is C, 60 degrees. Now we also have a few of the other answers all the way from 15 to 150. So let's get rid of the poll now. And the answer is 60 degrees. Well done. So why 60 degrees? Well, so I don't know if you were paying attention when I was playing around with the projectile motion, the FET before, but you might have noticed that when you launch at 35 and you launch at 55 degrees, that it landed in the same spot, and that's because those two angles were equidistant from 45. 35 degrees was 10 below 45, and 55 was 10 above. So the same thing's happening here, okay? 30 degrees is 15 degrees below 45. So if you want to land in the same spot, you have to launch at 15 degrees above 45, okay? And that's why it's 60 degrees, okay? 150 degrees wouldn't work, right? So yeah, it's got to be symmetric to 45 degrees. 150 degrees would send you in the opposite direction. So if you look at our graph here, they show you the trajectories. Okay, so you can see, again, 45 is always the longest, and then 30 and 60 have the same range, okay? Get back to the same point on the x-axis. And similarly, 75 and 15 end up back at the same point. Okay, so that's another one of these symmetries of projectile motion. Okay, that basically the motion up and the motion down, there's a symmetry between the upwards motion and the downwards motion. Okay, so now we're going to try another poll question. So have a look at this one while I set up the poll. And we've only got 3 choices here, so this is a little bit easier to set up this one. All right, so what do we have? So we have a destroyer, so this is a Navy ship of some kind, and this destroyer simultaneously fires 2 shells with the same initial speed. So notice that I drew these 2 vectors, these 2 initial velocity vectors, the same length, okay? But they're not the same angle, but they're the same speed, okay? And you're firing at 2 different enemy ships, right? And the shells follow the trajectories shown, and the question is, which ship gets hit first? Enemy number 1, enemy number 2, or they are both hit at the same time? All right, I think we're going to do about 10 more seconds on this one. So if you're not sure, go ahead and take a guess. Okay, 5, 4, 3, 2, 1. So let's have a look at the responses. Okay, so what do we got? So we have the majority, 157 people, think that it's C, okay, but there's a reasonable group that think that it's B. All right, so I think we're going to try this one again, but I'm going to give you a hint. Okay, so what I've done now is shown the cannonball and showed you basically the path up and down, so just the vertical path of the cannonballs, the 2 cannonballs. Okay, and one thing to remember is that the motion in the horizontal and vertical directions is separate. They're independent from each other. Okay, the only thing that's common between the 2 is the time. Okay, and what I want you to think about is, does it take longer for shell A to reach for the shell to reach point A and fall back to the sea, or does it take longer for the shell to reach point B and fall back to the sea? Okay, because that is going to tell you which one gets hit first. All right, so I'm going to start the poll again. Okay, so now that you know that hint, okay, what do you think? Basically, which of those 2 vertical motions would take longer? All right, I think we'll do 10 more seconds on this one. So go ahead again and guess if you're not sure. All right, 5, 4, 3, 2, 1. And let's look at the responses again. Okay, so it looks like a lot of people changed their minds, and now we have a much larger group for B, but still a reasonable group for, so the biggest group now thinks enemy 2, the ship that's further away, is going to get hit first. Okay, but there's still a reasonable group that think they're going to be the same time. So it turns out the answer is 2. Well done. So so the hint seems to have helped. Let's end the poll to get it out of the way. Okay, basically the idea is that the shell launched towards enemy 2 has a smaller initial y velocity. Okay, remember the speed was the same for these two, so the magnitude of these vectors is the same, but since the one launched at enemy 2 is at a shallower angle, it has a bigger x component and a smaller y component. Okay, and it's that y component of velocity that tells you how long you're going to be in the air, because it's the y component of velocity that tells you how high you go. And the higher you go, the longer you're going to stay in the air, because it takes a certain amount of time to go up and come back down. And so the one, even though enemy 1 is closer, okay, to get to enemy 1, they had to fire that cannonball higher, okay? And because it went higher, it took a longer time. So even though it's kind of a little counterintuitive because enemy 2 is further away, right? So you might think that therefore it takes longer to get there, but that cannonball spent less time in the air, right? Because it took a shorter time to go up and come back down again. Okay, so that's the kind of thing you have to think about when you're doing these problems. So how about another one? This is a related, slightly different setup. So I will do this one now. Let me just get this started. Okay, so now we have a destroyer fires 2 shells with different initial speeds. Okay, so these are different initial speeds now at 2 different enemy ships. Okay, and the shells follow the trajectories shown. All right, and again, the question is which enemy ship gets hit first. Okay, and the thing to realize here is that the maximum heights are the same. So the height for the shell that hits enemy 1 is the same. It's supposed to be the same as the height, okay, here. So the maximum height of the shell that hits enemy 2 is the same as the maximum height, okay? So think about what that means for how long the shell stays in the air. All right, I think we'll do 10 more seconds again. So if you're not sure, go ahead and guess. Yes, this has different initial speeds. So 5, 4, 3, 2, 1, and let's see. Okay, so now we have our majority think that it's C, that they're both going to hit at the same time. And then, but there's also a reasonable size group that now thinks enemy 1 is going to get hit first. Okay, and the answer is actually C. Well done. Okay, so why C? Why are they both hit at the same time here? Well, it's essentially the same answer as for the last one. Basically, they both have the same initial y velocity. How do I know they both have the same initial y velocity? Because they both go to the same height. And if they both go to the same height, okay, that means they spend the same amount of time in the air. So even though enemy 2 is much further away and that shell traveled a longer x direction, x distance, okay, what determines the time is the height, okay? So the time, so how high you go, right? Because it takes a certain amount of time to go up and a certain amount of time to come back down again, okay? And that's the same for these two here, okay? So again, this is kind of thinking through these things. It helps you hopefully get a better sort of familiarity with these problems. So now what I thought we would do is work through an example problem, because I think it's often useful to do examples. So this one is about football, okay, Canadian or American football. So what we have is a field goal kicker. So a field goal kicker kicks the ball at 30 meters per second at an angle of 25 degrees above the ground, which would be 25 degrees above the horizontal for us. And the crossbar of the goalpost is 3 meters off the ground, okay? And the question is, from how far away can she kick a field goal? Okay, I decided to make it she because there was a young woman soccer player who was kicking field goals recently for an American college football team. So, basically, we're trying to figure out how far away she can kick a field goal. And the idea is that basically, there's a maximum distance that she can be from the field goal posts. And if she's any further away, it won't go through the crossbars, okay? The ball won't be high enough when it gets to the goal posts, right? It won't be 3 meters above the ground when it gets here, and so it won't make it through, okay? So basically what we're saying is that there's a maximum distance that she can be from the goal posts, okay, so that the ball just clears the crossbar, okay? So Russell doesn't understand this game yet. It's I don't totally either. So here is the football. There it goes, and so this would be the distance where it just barely crosses, okay, here. So what we're going to do is go through and try and figure this out. So we're trying to figure out this distance, this maximum distance that when the football gets to the goalpost, okay, it just barely crosses. So now if you run into one of these problems about a sport and you don't understand the sport and what it means, you should always ask somebody, but even during a test or something, because I'll try not to write problems where you need to have any sports knowledge to solve them. All right. So what do you do? So just like with our 1D problems, the first thing you want to do is label things, draw a picture. So we already had a picture, so now I'm just going to add some labels here. So I put in my y-axis, which will be, so plus y, okay, is the vertical upwards direction, and plus x is the direction the ball is being kicked. Okay, I'm going to start at time equals 0, okay, and my football is going to have an initial velocity v0, and that launch angle is our 25 degrees. All right. So to make our lives easy, I started the football at the origin of my coordinate system. So that means x0 is 0 and y0 is 0. Okay. And then the very first thing I'm going to do is figure out the components of my initial velocity vector. So my initial velocity, v0x, I just take my magnitude, 30 times the cosine of the angle. I get my 27.2 meters per second. And then my initial y velocity is 30 times the sine of the angle, right, because it's opposite, and you get 12.7 meters per second. Notice they're both positive because you can see from the velocity vector the ball is being launched to the right and up. So they should both be positive. Okay, so that's where we start. Okay, so then over here, all right, what do we know for the ending? We don't know the final x position. Okay, that's actually something we're looking for. What would the final y position be here? Anybody want to put it in the chat? What would the final y position be for this problem? Yeah, it would be 3 meters. Good. The final y position would be 3 meters. Okay, because we're looking for the ball to be exactly crossing the crossbar. Okay, that's our final position, exactly crossing the crossbar. Okay, of the goalposts. Okay, and then that'll tell us, that'll be the y, and then we're going to find the corresponding x. So our final y is 3 meters. Okay, it's barely greater than 3, but we're going to set it equal to 3 as like the limiting case. Okay, you don't have to worry about the width of the football. Little things like that we're not going to worry about. Okay, so what do we not know? We don't know the final position in the x direction. We don't know the time. We don't know how long the ball took to get there. And we don't know the final y velocity. We don't know how fast in the y direction that football is moving at this point. We know the x velocity because it's the same as the initial x velocity, right? That will not change. All right, but right now, the one we're after is x, right? Okay, so that's the one we're going to try and solve for. So how do we solve for that? Well, so now we have to go look at those kinematic equations I introduced. Okay, and so I thought we would have a look. I'm not going to necessarily do this as a poll, okay, but I think I'm going to get you guys to think about it and put it in the chat. And the question is, which kinematic equation, or it could be more than one, which kinematic equations should we use or could we use to find x, the final position, which is what we're after? Okay, so what do people think? So we've got some votes for A, we've got some votes for B and C. Okay. All right, lots of votes for B and C, some votes for A, some votes for A and B. Okay, so let's think about what we have here. Okay, if we look at A, what do we have? We have the initial y velocity. Yes, we have that. We have the initial and the final y. Yes, we have both of those. So what could we get? We could get the final y velocity from that. Okay. But that's not going to give us x. We'd have to do more work, right? Then with the final y velocity, we'd have to use one of these other equations, maybe d, to get time. And then once we had time, we'd have to go back over here to c, okay, to get x. That would work. That's 3 steps. The other way to do it, and I'm going to show you both ways, actually. So the other way to do it is to start with this one, okay, which is to look at the y motion, because we do have the final y, we have the initial y, we have the initial y velocity, and we know g. So we could get time, and then using time, we could get directly to x with this equation. So let's try that first, and then we'll also try it the other way, and so you can compare. Both of those are valid ways to do it. Okay, so my Wi-Fi is being a little flaky, so hopefully it hangs in there. Okay, so all right, so we're going to start with this one. So let's plug in some values. So what do we have? The final y position is 3 meters. The initial y is 0. The initial y velocity is our 12.7 meters per second. And we plug in minus 1/2 g t squared. All right, and right away, you can see that that is a quadratic equation. All right, so what I did was I to solve a quadratic equation, we need the quadratic formula. So what I did was I put everything on one side of the equation. So I took my minus 1/2 times 9.81, which becomes the 4.901, and moved it over to the left-hand side. I took my positive 12.7 times t and moved it over to the left-hand side. That became minus 12.7. So now we're basically just doing some math. We've got our quadratic here that we need to solve. And at this point, I would say go look up a quadratic equation solver online. You don't necessarily need to do these by hand. Even on a test, you can go use a quadratic equation solver. That's okay with me. Okay. So, and then, because I'm not testing you guys on math, at least not to that extent, okay? I mean, you do still need to get your math right to get the answers right here, okay? But if you go and use a quadratic equation solver here, like I did, you end up with 2 answers, okay? T equals 0.263 seconds, and T equals 2.33 seconds. And you might say, well, 2 answers, what does that mean? Well, basically, the reason they're valid answers, both of them, we saw this actually with one-dimensional motion, they're both valid answers because the ball reaches this y position 3 meters twice, okay? It reaches 3 meters right after it's launched, after 0.263 seconds, so that's the shorter time, the first time, and then you go along and it reaches 3 meters again, okay, near the end of its path, and that's the 2.33 seconds. So you do have to go and look at and think about your 2 times and choose the right one, okay? Do I want the time right after it's launched, or do I want the time right before it's landing, okay? So, and then once you do that, I'm gonna choose the longer time, and I'm going to plug the longer time now into my x equals x0 plus v0 xt formula, kinematic equation. Okay, and so there's my initial x velocity, the 27.2, times the 2.33 seconds, and I get that my final answer is 63.4 meters. Okay, so that's how far away she can kick. Okay, that's a big number. That's probably on the maximum. She must be a very good field goal kicker. Okay, but it's about the right order of magnitude if you think about how big a football field is. Okay, this is on the order of I don't know, 75, 80 yards. So it's a long field goal, but it's a reasonable order of magnitude answer. And so that's our final position. So that's how far she can kick a ball. All right, so just to show you, we got a couple more minutes left, how to do it the other way. Okay, so like I said, we could have used these 3 kinematic equations instead. All right, so let's do that. All right, so we're going to start with the y as a function of position. Again, you just plug in your values. So now we're trying to solve for the final y velocity. Okay, and so we plug in our initial y velocity squared minus 2 times g, and then the change in the y position. And again, you get 2 answers because we've got the vy squared. You get 2 answers, plus or minus. And you might say, what does that mean? Well, just like before, because the ball reaches this y position twice, right, you're going to get 2 different velocities. So the plus answer here is the y velocity when it's on its way up, about here somewhere probably. And the minus velocity is the y velocity when it's on its way down. Okay, and remember they're supposed to be the same because you're at the same height. So we would expect them to be the same, but one's positive and one's negative. So which one do we want now for our final position? The positive one or the negative one? Anybody guess? Which one do we want? That negative one. Good, because we're going downwards there, right? So we want the negative one. So now we take our Vy equals V0y minus GT formula, solve for time, which is what we're after right now, and we're going to plug in the negative velocity because we know our ball is going downwards. And if you do that, you get 2.33 seconds, and that's the time we solved for the other way for the time when the ball will be just above the field post here. Okay, So we get exactly the same time, and then you would just go back, you would just plug that time in, right, to this formula, just like we did here. Okay? So that's what I wanted to show you for today, was to give you a nice example of how to do a typical projectile motion problem. So if anybody has any questions about any of that, okay, I'm happy. Otherwise, we're basically done for today. I'm happy to answer any quick questions people had about that. Yeah, so there's always more than one way to do these problems. So you could have done it either way, and it would have been fine. Yeah, so these will be in the next sapling homework. We'll have projectile motion and circular motion. Like I said, we'll do circular motion on Friday. All right, I'm going to stop the recording.